Welcome back. It's now week 7. So we just need to finish up some things in order to have our test. So today's session is probably going to be relatively short. I just want to cover the few things that we haven't covered yet from this batch of slides. If we were doing this as a seated class, now is the time when I finish this stuff that I would go back and review all of the things we've talked about so far this semester. But since all of this is on video, and you can go back and review this stuff whenever you want, I'm not going to bother doing that. So I'll finish up what we need to finish up talking about, and then pretty soon I'm going to post the test. So I'll definitely let you know when that happens, and you'll have time to work on the test. So and multiple attempts. So what you're probably going to do is take the test. I encourage you to take that early on, as soon as it's posted. And then if you feel the need to go back and review some of the videos because you weren't too sure about some of the things, then your second attempt should go much better. So let me stop my video here, and I can share with you what I'm looking at. So we've got Blackboard, and we'll pick the course as usual. I just like to do this so I'm sure everybody knows how to get to the content that I'm posting. And lessons, and we're working out of slides 2 here. So by the time you watch this, 7th lecture will be sitting up here. I don't have that yet because that's what I'm recording right now. So you click on the slides, and we've been through most of these. Let me open that up. And what we were doing was going one by one through a list of inputs. So we've already talked about thermistors, potentiometers, switches, data streams, AC generators, DC generators. And what's not really listed there is Hall effect. Those really they're not generators. But I covered them when I covered AC generators because they're used for the same sort of purposes, right? Measuring rotation a lot of times, rotational speed. So we left off with basically oxygen sensors and air-fuel ratio sensors. So let me scroll down to that. And let's see. So we did air-fuel ratio, then we did Hall effects, and this was the last slide we looked at last time. So if we move on forward, our next topic is pressure sensors. And there's 2 kinds I'm going to talk about. There's voltage-based, which are the most common, and then frequency-based, which these really don't even exist anymore. I'm just going to mention them briefly. It's something Ford used to use years ago. So voltage-based ones, again, we can break those into 2 categories. We've got piezoelectric, which is a crystal that generates a small voltage when it's squeezed, when there's pressure on it. Or in the example of a NOx sensor is called a tuned accelerometer. And that generates a small voltage when it vibrates, but only when it vibrates at a specific frequency. That's why they call it tuned. It's basically when it vibrates at the frequency resembling engine knock, that's when it generates the voltage. In order to test these, believe it or not, you can tap on the engine with a hammer while watching the NOx sensor voltage, and that vibration in the engine block will actually cause that NOx sensor to put out a small voltage. Most pressure sensors don't generate their own voltage necessarily. They control some sort of voltage, right? So PFE, DPFE, those are Ford things, pressure feedback EGR or differential pressure feedback EGR. And they were used to more accurately measure exhaust gas recirculation flow by looking at either pressure in that EGR tube, pressure in a tube hooked to the exhaust, or pressure in two tubes up to the exhaust, and then measuring the difference between those two. Probably most common, MAP sensor, but also fuel tank pressure sensor. They frequently look very similar. There are fuel rail pressure sensors. There are pressure sensors used in seats for supplemental inflatable restraint, in other words, airbag systems, to know whether or not there's somebody sitting on the passenger seat and whether it's a child or an adult. So you may find these all over the car. They use a 5-volt reference, really similar to a potentiometer. So if you look at the wiring to one of these pressure sensors, we'll just work with a fuel tank pressure sensor. You know, most cars now use them for the evap monitor, not all, but most. And fuel tank pressure sensor is a voltage type pressure sensor, and it's like a potentiometer. It has 3 wires, and those wires are the 5-volt reference, just like a potentiometer, a signal return or ground or low reference. Pick any one of those words. They all mean the same thing. It depends on the car manufacturer, right? Ford likes to call it signal return. GM likes to call it low reference. Other manufacturers just might call it sensor ground, but it's going to be a ground wire right back to the computer. And the third wire is the actual signal wire. So that's the one that changes based on the pressure applied to the sensor. This is a typical MAP sensor, and the drawing's not necessarily perfect, but you know, remember when we went to the potentiometer, we talked about that. Inside the computer, whichever computer we're talking about. So let's say this is a MAP sensor and we're talking about the powertrain control module. So here we've got the 5-volt reference voltage regulator. That is sending 5 volts, a very precise 5 volts out to a whole bunch of different sensors. So this is one of the sensors getting that 5-volt reference. It has the sensor ground right back inside the computer, right? So 5 volts and ground. If you put a voltmeter across that wire and that wire, in my experience, you'll get almost exactly 5 volts, no matter what's going on in the car. So it might be 4.99, 5.02. It's usually within a couple hundredths of exactly 5 volts. And the advantage here of operating on 5 volts, right, is battery voltage is constantly changing. The engine speeds up, the alternator's going faster, battery voltage goes up. You put on a heavy load, headlights, rear window defroster, the AC blower, you know, battery voltage drops. But this 5 volts just stays the same through all of that, right? So the computer always has a precise reference to work off of. And the signal wire is some percentage, right, of this 5 volts. So it could be 1 volt, 2 volt, 3 volts, 3.7 volts, you know, up to possibly somewhere near 5 volts. It's going to be some portion of that returned back to the computer. So we're providing 5 volts and we're going to get some of it back here. So what you can think of this thing right here as a little digital voltmeter, right? So digital voltmeter, this would be the red lead, essentially, measuring the voltage here. And this would be the black lead, right? It's connected to the ground. So this here is the voltmeter, and it's measuring the voltage on this wire. And that voltage is going to change based on how much pressure is feeding in through this port. So diagnosis would be really similar. First of all, if we go back to what I said about potentiometers, right? It would never be normal for the computer to see 0 volts. that wouldn't be right. If the computer saw 0 volts, then either this wire here is broken, right? So the sensor's never getting the 5, or this wire here is broken, so it's never making it back to the voltage sensing circuit, right? So if we see 0 volts, there's a problem. Could it be the sensor itself? It could be, yeah, but I think it's more likely we've got a wiring problem on either the 5-volt reference or the signal wire. We should never see 5 volts. This signal should always be only part of that 5-volt reference, right? So if it's 5, it probably means this ground wire is broken. So there's no voltage drop through this circuit, and the entire reference voltage is on the signal wire. So that's a quick and dirty look. You know, you think there's a problem with that sensor. What could go wrong? And this applies to almost any sensor, right? Let's talk a little bit about diagnosis. So if there's a problem with this map sensor, the signal is incorrect, there's 3 things it could be. It could be there's something wrong with the sensor. It could be a problem with the wires, or it could be a problem inside the computer. That is the entire realm of 3 things that could be wrong. So, how do I check this? Well, I can check both the wiring and the computer kind of easily, and you have to be careful here, all right? But if I unplug the sensor, so I disconnect that connection right there, what should my map signal be back at the computer? It's going to be 0 volts, all right? There's no way I'm going to read 5 volts back. If I still read something with that sensor unplugged, then I've got some sort of a connection between these 2 wires, a short, right? That wouldn't be good. So I unplug the map sensor, I get 0 volts like I expect to get. Okay. What happens if I unplug the sensor and I connect this reference voltage wire right back into the map signal, right? So this is what I have. These connected right together. And this is where you have to be careful. You have to make sure you understand what you're doing. What should this read now? That should read 5 volts, or exactly what's being supplied on this wire should wind up on this wire, right? You've connected them together. What does that tell me? That tells me a lot. It tells me, one, that this wire is not broken, right? And it tells me this wire is not broken. It also tells me that the computer is able to see that voltage. I'm feeding it in, the computer can see it. You could even go so far, if you wanted to test the ground, right? You could take a AA battery and hook it right there and feed that 1.5 volts, right, from the AA battery into this thing, and you would see 1.5 volts at this computer, telling me that the signal wire and the ground wire are both good. Now, that's obviously not the only way to check wires. Typically, what they'll have you do, right, they'll have you come out and check the voltage here, right? What do I expect to see there? I unplug the sensor, right? The end of this wire hanging out in the open, I expect to see 5 volts, all right? I come here and I check, I expect to see a good ground. So I could use an ohm meter between here and another known good ground. I could use a voltmeter if I hook the voltmeter to this wire and it reads 5 volts, then I know not only is this wire good, but this wire is too. And then the other thing I could do is ohm meter check this wire. But like I said, and tread carefully, right? If you feed this 5-volt reference wire directly into that signal wire, and 5 volts is read right here, it tells you this whole loop is good, and it tells you that that voltage sensing circuit is good, and the voltage regulator is good. The only thing you have left to check is the ground. How do you check the ground? Well, like I said, voltmeter, red lead there, black lead there. If it reads 5 volts, both this wire and this wire are good. If you've checked those things, now you know the wires are good, you know the computers are good, you can absolutely guarantee yourself that replacing the sensor will fix the problem. And how long does it take to check this stuff? 5 minutes maybe? So there's no need to guess and throw parts at stuff or throw a sensor on it when you're not sure. So the frequency type sensor, I'm only going to spend a minute. The old Ford map. What it did, we talked about square waves already, but the frequency would change based on the pressure applied instead of the voltage coming out of it changing. So in order to measure that, you would either need an oscilloscope or you would need a meter that does hertz. But they didn't give you any specs for what the hertz ought to be. They had a map sensor tester that converted to voltage you could plug into a voltmeter. Most techs, honestly, carried a map sensor in their toolbox, and they tested it by plugging it in. It was just way faster. That's not really a recommended necessarily way of diagnosing, just slapping parts on, but in some cases, it made sense. So now, let me just talk about see if I can edit this here. There we go, enable editing. All right. All right. We already talked about that. I'm going to just create a blank slide here a second. Somehow I managed to mute myself there. So what I'm trying to do here, I hit Control M, which is the same for inserting a new slide. Let's see if I can actually insert one here. There we go. That was a little weird. Okay, get rid of that, get rid of that. I just need basically some place to work. All right. I want to talk just briefly about this Ford PFE was like the map sensor we just talked about, but the DPFE, the differential pressure feedback EGR sensor, they're out there. You might run into them. So I'm going to try to make this really simple. Here is the exhaust, and here is the intake, right? So what does an EGR, exhaust gas recirculation system, do? It recycles some of the exhaust, right? Let me label these before it gets too confusing, right? So we'll call this exhaust, and we'll call this the intake. I'll move that down a little bit. Just a little too close. Okay, so exhaust manifold, intake manifold. what does the EGR valve do? I'm just going to draw right here, okay, and just put a little connection. We'll call that the EGR valve. That is a horrible drawing, I know. Just trying to get the point across. So, all right, and then from the EGR valve, a pipe, right? A tube. So when this EGR valve opens, exhaust can flow from the exhaust manifold into the intake manifold. Get rid of that. Now, the early EGR systems, they had a potentiometer on top of the EGR valve to measure how far open the valve went, trying to determine how much exhaust gas is flowing from the exhaust into the intake. And the computer's trying to control this, right? But in order to control it, it needs that feedback to know, all right, I'm opening the valve, but do I need to open it more? Do I need to open it less? How much EGR flow am I actually getting? Where am I at? And so measuring the opening of the valve wasn't good enough. And the reason for that is passages plug up. You could have the valve wide open and have zero EGR flow, and the computer would have no idea, right? Because the passage is plugged. So what they eventually did forward, and this is going to be kind of goofy, but this passage from the EGR valve to the intake, let me just redraw here a little bit bigger, right? It had two tubes sticking up out of it. Actually, all right, I'm going to get rid of that. I'll draw it down below. I don't have enough room up here. I'll draw it down below here, all right? So here's that pipe that goes from the EGR valve to the intake. And two tubes sticking up out of it. Now, students who are used to my seated lectures know that my drawings are legendarily horrible, so you guys are getting to see some of that now, right? In the middle of this tube was a little orifice, right? A little hole, right? Fixed orifice. And then these two tubes were connected to the pressure sensor. So it was called a DPFE, which was either differential pressure feedback EGR or delta, which kind of means the same thing, right? Measuring the difference in the pressure in this passage here, right? This one and this passage here. So with the EGR valve closed, okay, the exhaust pressure comes in from the exhaust here, and it goes through that orifice, and the valve would be over here. I kind of drew that wrong. The EGR valve should be here, right? On the intake side. Talk about confusing, I know. So the EGR valve is sitting over here. This thing here. Doesn't look like much of a valve, I know. So if it's closed, then, this entire passage here, right? This side of the orifice and this side of the orifice, it's dead-ended here. That pressure is going to be the same throughout this entire tube. And that means that the pressure going up this pipe is going to be the same as the pressure going up this pipe. So when the pressure sensor looks at those two pipes, it sees they're the same. It knows there is no EGR flow at all. When the EGR valve opens, all right, so this guy here opens up and, allows flow into the intake manifold. right? So, over here is the intake manifold. Allows flow through that valve and into the intake manifold. That means that there's going to be more pressure against this side of the orifice than there is over here, because this side of the whole chamber has a big hole in it leading to the intake manifold, which is pulling that exhaust out, right? So the pressure on this side is going to drop way down below what the pressure is on this side, because that orifice is making a restriction. It's not allowing the exhaust to flow out of here as fast as it's allowing to flow out of here. So because of that, this is nasty looking stuff, right? Because of that, the pressure on this tube is lower than the pressure on that tube, and the sensor puts out a voltage based on that differential, right? So the higher the difference, the higher the voltage. And the computer can use that to determine EGR flow in a much more accurate method than they can by looking at just the position of the EGR valve, whether it's open or half open or fully open or closed. Because as soon as that EGR passage starts to plug up, that EGR position sensor is basically useless. All right, so I'm not going to say this is the ugliest drawing I've ever made, but I'm used to drawing on a big whiteboard with my hands with all kinds of room. And so, this video I may have to destroy after you guys are done watching it because it's pretty funny looking. Okay, get rid of that. Let's see what kind of questions we have. So what kind of signal does a voltage type pressure sensor produce? And if I ask you a question here, there's a good chance you might see it on the test, right? So what's the answer? Voltage type pressure sensor produces a varying analog voltage that is dependent on the pressure applied to the sensor. So it's going to be somewhere between 0 and 5 volts. But like a potentiometer, it really should never reach 0, and it really should never reach 5. So a more realistic range for you to expect to see on that sensor would be, say, from half a volt to 4.5 volts. Because if it sees 0, it takes that as something's wrong. And if it sees 5, it takes that as something's wrong as well. What type of signal does a frequency type pressure sensor provide? Well, that's just a varying frequency. The voltage is the same. It might be 5, 0, 5, 0, 5, 0. How rapidly it switches will change based on the pressure. And how many wires does a pressure sensor have? Okay, so let's go back to this guy here, right? We talked all about this. So 1, 2, 3, just like a potentiometer. Okay. Other sensors. Well, there are maybe a lot of other sensors. Some things that I don't have in this set of slides, maybe we'll get to later in the semester. Parking sensors, proximity sensors, lane departure, kind of radar sort of things like that. Don't have that in this slideshow right yet. So the only other sensor that I have in here that I want to talk about is the mass airflow sensor. Okay, I want my keyboard work. Let me show you something here. See, it says uses 5 volts. This is something I thought I changed a long time ago. So let's start with changing that. All right. It does not use reference voltage. It uses battery. Whoops, I don't want that. I don't need that. Battery voltage, which is 12 volts. All right. So mass airflow sensor. Let's first talk about what the purpose of this sensor is and where it's located, okay? So located in the intake airstream of the engine, usually or frequently on an air inlet hose between the air cleaner and the throttle body. It may be separate mass airflow sensor, or it may be a mass airflow sensor and an intake air temperature sensor combined. So the easiest way to find this out, if it's just a mass airflow sensor, there will probably only be 3 wires. If it's a mass airflow slash intake air temperature, it's likely to have 4 wires or 5 wires. So if it only has 3 wires, then you're going to find an intake air temperature sensor somewhere else. So we just made this correction, right? So if I hook up to this thing with a voltmeter, and this, there are 2 kinds of this sensor too. If I hook up with a voltmeter, I'm operating on the assumption that the max it can put out is 12, right? So the output voltage or the frequency is based on airflow through the sensor. This is something, I have a worksheet in the lab, and we actually drag out an old-fashioned oscilloscope, a lab scope, an analog one, and you can see really clearly the difference between the voltage type and the frequency type. So we'll do that this week or next week. On the voltage type, if there's no airflow through it, there is no voltage coming out of it. So there's no like default, bottom level on this sensor. So here's the way it works, and this is a little bit weird, right? So most of them, they have a pair of wires, a hot wire and a cold wire. So let's talk about what happens when air flows over anything, right? You're familiar with the concept of wind chill, especially around here. And so you know that when the wind is blowing more strongly, it takes heat away from your body faster. So it feels much colder. So the wind velocity can sort of be measured by how fast it takes heat away from something. Now, we're not just worried about velocity when it comes to a mass airflow sensor, right? The name is mass airflow. So we're actually concerned about how many molecules are passing through that sensor. We're not really concerned about how fast they're coming through. It's how many, right? So mass airflow sensor, its job is to tell the computer how much air is coming into the engine, so the computer can use that information to decide how much fuel to deliver to the engine to get the right air-fuel ratio. It is the primary input on systems that use it for fuel control calculations. There are others that tweak it, throttle position, or accelerator pedal position. Obviously, if the driver has his foot on the floor, then we are going to add additional fuel for the extra power. If we are in cruise mode, we might add a lot less fuel for better fuel economy. If the engine's cold, it's going to add more fuel. But the number one, input, that's the main piece of information the computer needs to determine fuel flow, is how much air is coming in through that sensor and therefore through the throttle body. So here's a picture, right, of the hot wire and the cold wire. We've already talked about thermistors, so let me again, okay, this might get stupid again, try to do a new slide, right? Yeah, see, that was easier that time. So I got a new slide, so I can do a little bit of drawing again, a little bit of ugly, nasty drawing. When air is less dense, molecules are far apart. So these molecules are flowing in through that sensor. Here's my hot wire right here. And these molecules come and they hit that wire. And they hit that wire. And as they hit that wire, they absorb heat from that wire. They take heat away from that wire, and then they move on through and into the engine. So if there's a small amount of air flowing in, and this is not by volume, this is by mass, right? So density matters, right? If there's a small amount of air flowing in, there's a small number of molecules of air hitting that sensor and taking heat away. So it does not take a whole lot of current. Well, I didn't want to erase all that, right? So again, here's our wire. We're trying to keep that hot, and here's the sensor up here, right? The sensor's job is to provide enough current to that hot wire to keep it at a constant temperature. So as more molecules of air start hitting that wire, either because somebody has stepped on the accelerator pedal, right? So that's going to cause a whole lot more air to hit that wire, more molecules. They're going to take heat away faster. This module is going to have to increase the current to that wire to keep it at a set temperature. That current, that amount of current is then translated by the electronics in this sensor and sent out to the PCM as either a variable voltage or a variable frequency. So the actual operation of the sensor, the hot wire, and keeping that wire hot is pretty much the same, whether it's a frequency type sensor or a varying voltage type sensor. The difference is all in the electronics here. How they've chosen to output a signal based on the current flow it takes to keep that wire at a fixed temperature. So the nice thing about this, right, why this works so well, not only does it account for the volume of air coming in, right, because more air coming through, like if you open the throttle, means more air hitting that sensor, more molecules of air hitting that sensor. But it also accounts for the density, right? So different barometric pressures, different altitude, different temperatures and humidities, all of that affects how that air takes heat away from that wire. And all of that affects how much fuel is needed too. So it's really kind of neat that it automatically compensates for density and things like that, because it's really measuring not just the volume, but the thickness, if you will, or the density of that air because of the way it works. I'm not even going to bother with this thing here. We'll just skip that slide altogether. You can look at it if you want, but notice, that this sensor does not sample all of the air. There's a lot of air that passes through this sensor without touching the hot wire, but it samples a percentage. So let's say that this passage here is 10% of the entire, diameter of the sensor. Then whatever the sensor measures going through this passage, well, all it's got to do is multiply by 10 to know what the total flow through the entire sensor is. So even though it's only measuring what's going through here, it can extrapolate, interpolate, whatever word you want to use, in order to kind of come out with a signal that tells the computer how much air is flowing through the whole thing. So back to this idea of varying voltage or varying frequency. This is something that's just much easier to show you in the shop. If I tried to show you here, I mean, Let's see, did I lose my, there's my blank slide, right? So if I say, just briefly, that this is 0 volts and say up here is 12 volts, right? The voltage type sensor is going to wander around based on airflow, right? So you stomp on the accelerator, voltage goes up. You take your foot off the gas, it drops back down. Steady cruise, you're going along like that. You know, hit the gas, whoop, up it goes, right? So you can just use a regular DC voltmeter and watch this. You could write yourself a chart for different engine RPMs and loads and figure out, based on the voltage, how many grams per second are flowing through this thing. Typically, when you look at this on a scan tool, it may not even give you voltage. It may just give you grams per second and not even tell you what the actual voltage is. But you can stick a voltmeter on the signal wire from this thing. You can see what the actual voltage is, right? The frequency type, which they look the same on the outside, so you never know what you're going to get. The frequency type, so it's a square wave. It turns on, it turns off, it turns on, it turns off. And what happens when you hit the gas is that frequency gets much, much higher. So the on and offs come much closer together. This is really a horrible drawing, I know. It's hard to draw with a mouse when you're not used to it. So the frequency increases, and the voltage obviously is still 12 and 0. So voltage doesn't change at all. It's just flipping up and down more rapidly with higher airflow than it is with less airflow. I gotta get rid of all this stuff. That's pretty ugly. So we should get a scope out and check out a few different cars. I happen to know what some of them are, but others you don't really know until you put the scope on it and see what happens. We don't need the scope, like I said, on the frequency type. You can use a meter that has hertz. Okay, so let's just summarize this entire talk about inputs, right? Many different types of sensors are used, right? We got thermistors, potentiometers, we got pressure sensors, we got mass airflow sensors, we got oxygen sensors, airflow ratio sensors, both single cell, which is 4 wires, or dual cell, which is 6, all kinds of different ones. Pressure sensors, they can provide an analog voltage, digital voltage, or frequency, right? So analog voltage, it's moving around somewhere between 0 and 5. Digital voltage, maybe it's either on or off. Or frequency, we just talked about that, right? The computer converts it can handle all of these different types of inputs and converts them all to little electrical impulses that are stored in memory or that are used, right? Sensor voltage and or frequency is based on some external conditions, pressure, temperature, position, something like that, right? So hopefully this is not too confusing. I really prefer the in-person classes because you can ask questions, and it's obvious to me when I need to explain something in a different way. This does not provide that. So once again, that is always part of my invitation is you can ask me questions during the lab if there are things you're not quite getting watching these videos. So let's talk a little bit about the test. I will be announcing a test really soon, right? So by the time you watch this video, I may have the test ready and I may be ready to post it. When I do that, I'll tell you by email. I'll tell you how long you have to complete it. And I usually give multiple attempts. So again, my suggestion, right, is that after you've watched all the videos, you take the test. Now you know what's on the test, right? You go back through these PowerPoints, you go back through the videos if you need to, and then retake the test. Odds are you're going to do a lot better. So good luck on that, and I'll see you in the shop this upcoming week. And there's a couple things. I want to spend some time with scan tools on. Some of you did this, so some have not. More on looking at oxygen sensors, looking at air fuel ratio sensors, seeing the difference between the upstream sensors and the downstream sensors, right? So all of that whole measuring the oxygen content in the exhaust gas. I want to look at that on a scan tool with you on different cars, because a lot of them are different. And the other thing is that would be good is to check out the mass airflow sensor on multiple cars to see what kind of signal those particular sensors put out and what they're affected by. You know, how do they change when airflow through them increases? So that's it for today, and I'll see you in the shop.